so now we're gonna be going over skeletal formulae. As a follow-up to the previous videos and to help clarify some things. Skeletal formulae is pretty useful because it allows us to make things a lot less verbose, a lot less heavy. It takes up a lot less space on the page, and just generally makes things a lot easier to read. So the whole point of this is to allow you to be able to draw your own skeletal formulae for any given molecule. And if you do see a skeletal formulae of a compound, you'll be able to identify how it actually looks like. So we can start off with an example. If we take, say, pentane. Pentane is C5H12, and it sort of looks like this. It has 5 carbons arranged like this, and each carbon has single bonds attached to hydrogens until their outer shells are all completed. So, for example, in the case of this carbon on the end, it has 3 remaining spaces, so it is bonded to 3 hydrogens, whereas for this one, it's already bonded to 2 carbons, and thereby will only have 2. So this drawing in itself is a bit heavy. It's a bit wide, it takes up a lot of space, so one of the first thing we can do is to eliminate all hydrogens from it. So what we do here is essentially assume that each carbon atom will be fully bonded to hydrogen atoms when possible. So we can lower this down to just this. Now, the next thing we want to do is to go one step further and to remove all carbon atoms from it. But if we just did that, it would be a bit weird, and it'd be a bit it wouldn't be that good if we just drew a line like that. It wouldn't be very clear. We wouldn't be able to tell that there were 5 carbon atoms within it, or if there were 2, or if there were 4. So what we have to do is create kinks in the line. That's what you have to do for skeletal formulae. Whenever 2 carbon atoms are joined by the same bond, whether it's 2 in a row, whether they be single bonds or double bonds, you have to form a kink in the line. So in the end, pentane would be shown through this. This represents pentane. The same can be applied for any given molecule. So say we take another hydrocarbon. Say we just randomly drew one. Say we just took carbon. Oh, oopsie. Say we just took carbon here and triple bonded to another carbon, single bond, another single bond, and then a final double bond. And so then we know that each of these are bonded to as many hydrogens as they can. So we take 1 hydrogen on the end for here. This one is already fully taken up. This has 2 spaces, so we draw in 2 hydrogens. This is 1 space, we draw in 1 hydrogen, and this is 2. So as in the same way, we assume that all hydrogens are taking up spaces when they can, so we get rid of the hydrogens. So this just leaves us with carbon. And now we remove the carbons, so it would just start off as a triple bond. This is our final skeletal formula state. We draw 3 triple bonds, and now it's a single bond next, so we extend this. But here we have 2 single bonds, so it once again wouldn't be very clear if we kept on drawing the straight line. If we kept on drawing the straight line, it wouldn't be clear as to whether there were 1 carbon atoms there or whether there were 2. So instead we take 2 and draw it kinked downwards, and we end up with a final double bond. So instead we can tell that there are 1, 2, 3, 4, 5 carbon molecules in total. Carbon atoms in total. The same can be applied if you try to draw a molecule, any given molecule, that's not only a hydrocarbon. So say we had a simple amide. Say we have, so you have carbon bonded, double bond to an oxygen. NH2. Say we have something like that. The 2 cases where you actually draw in hydrogens are when they are bonded to an atom that is not carbon, because in that case we can't assume that its full outer shell is taken up. With the second case being when it's necessary to specify whether the hydrogen atoms are actually above or below the molecule. If it were above, you would draw an isosceles triangle that was filled in like this. If it was below, we would draw one that was the same but instead dashed. So say we had carbon here. we could assume that there were two hydrogens here, but we wanted to specify whether they were above or below. If we drew this, it would mean that they were both above. So in this case, if we looked at it sideways on, we could see that hydrogens were above it. If we drew them instead with dashed lines, or say one dashed line, we can see that in fact this hydrogen on top was above the central carbon, whereas this was below. So this hydrogen would be above, whereas this one would be below. So this is necessary sometimes. So say we go back to this amide. Let's get a new layer. So we go back to this amide. Oh. Now we want to apply it to skeletal formulae. So what we actually do is we keep in oxygen and nitrogen because those aren't carbon and we want to keep those in. So we take away the hydrogens if we can, of which there are none here because we don't know what's around here, so we just keep it all in. The hydrogens that are present aren't bonded to a carbon, they are instead bonded to a nitrogen, so we can keep those in. So we keep that as such. So instead we remove this carbon, so we're left with double bond here, an oxygen, and into a single bond of nitrogen with two hydrogens leading off it. So something like that would be directly applicable to it.